Okay, dear students, what comes next is solving this first order differential equation by using Laplace transform. In fact, initial condition is also given to you. So let's see how we can do or how we can solve this one. And I would like to thank you, all of you, for subscribing the channel first. So when I directly go to the solution, what you need to do is you have to introduce Laplace both sides, okay? So as you see, just have Laplace here for dx by dt, and also Laplace for each of these two is a power of minus t and Laplace of y, minus of Laplace of y. And as I told you, the Laplace of the first derivative is s times x minus x at 0, but know that student, capital X is x of s. Capital X is x of s. Remember that the Laplace of f was capital F of s. So now when I use capital X, I mean the Laplace transform for small x, okay? Minus, this is x at 0. X at 0, we wrote f at 0 in the case of Laplace of derivative of f. So now small f was used, now small x is used. X at 0 is equal to the Laplace of e is a power of minus t is 1 raised plus 1 minus Laplace of y, okay? Laplace of y is capital Y, or you may call it y of s. So when I use capital X, I mean x of s, and when I say capital Y, I mean y of s. So here I have, we know what Sx is. Look, Sx is here, and we know what x of 0 is. It is 0, so Sx minus 0 is Sx, which equal to 1 over s plus 1 minus y. So you have to keep this as your first equation. And when you go to the second equation, students, look, the second equation is given here. So again, have Laplace both sides as you did here. So the Laplace of dy over dt is equal to 3 times the Laplace of e is a power of minus t plus Laplace of x, as it is written. So the Laplace of dy over dt, as you did before, is the same as s times y, okay, capital Y, because it was s times f of s in the case of Laplace of f. Now s times y of s, or y can come minus, used f at 0, now it will be y, small y at 0 is equal to, now what's happening here is 3 is taken as common out, so Laplace of e is a power of minus t is 1 over s plus 1, so 3 times 1 is 3, 3 over s plus 1 can come, and the Laplace of x is x of s, or capital X, right? So capital X is used. So we know that y at 0 is 1, it's already specified here. So sy minus 1, as you see, sy minus 1 is equal to 3 over s plus 1 plus x can come. So students, x is the Laplace of small x, whereas capital Y is the Laplace of small y. Know that small x and small y are, you see, the functions we are looking for, because these functions are functions of t. We are looking for small x and small y, which are supposed to be written in terms of t. But here capital X and capital Y are Laplace transform of x of t and y of t, small x of t and small y of t, okay? So now let's try to combine these two and solve these two equations, okay? So what comes from the first one is y is equal to 1 over s plus 1 minus sx. Directly from this one can obtain capital Y to be 1 over s plus 1 minus sx. So I'm now going to substitute this in place of what? This y, okay? So after substitution, sy minus 1 is equal to 3 over s plus 1 plus x. I just took this directly from this expression. So in place of this y, I'm now going to put 1 over s plus 1 minus sx. Look, here it is. So in place of this y, I'm having 1 over s plus 1 minus sx. So this minus 1 follows is equal to 3 over s plus 1 plus x. So now let's try to multiple each of these and collect like terms together. I'm having x here, x2 here. So let's now solve for x. So as you are doing this is going to be s over s plus 1 minus s minus 1 minus 3 over s plus 1, x into 1 plus s squared. So what has been done here is those like terms are collected together. So take this minus sx to the right, it will be x into 1 plus s squared, because s times minus s is minus s squared. So minus s squared when it's taken to the right will be plus s squared. and shifting this 3 over s plus 1 to the left, to have minus 1 at the beginning, and this is s over s plus 1 minus 3 over s plus 1. This can come. Now we need to simplify this. Basically these two share the same denominator, so s minus 3 over s plus 1 minus 1 can come. As you see, s minus 3 over s plus 1 minus 1 is equal to x into 1 plus s squared can come. So we can now take 1 plus s squared to the left, right? Dividing the whole expression by 1 plus s squared. But before that, we need to simplify this. Take s plus 1 as the least common multiple, and you see, take s plus 1 as the least common multiple, and s plus 1, s minus 3 over s plus 1 minus 1 makes negative 4 over s plus 1. But dividing this by 1 plus s squared, this 1 plus s squared comes as a denominator. It can be shown. So now we have to decompose this. So this decomposition basically is done just simply taking a over s plus 1. Look, a over s plus 1 plus. This is not factored in the set of real numbers, so you will take bs plus c. So bs plus c. So the unknowns are now a, b, and c. So we have seen a lot of times how we can decompose rational expressions. So using that, we can simply obtain a to be negative 2, and b to be 2, and c to be minus 2. Okay, you need to recall that decomposition technique. And from this, the following can follow. Look, mind you, x is capital 1. I'm not looking for capital X, rather a small x. But there is a strong relationship between these two. Capital X is the Laplace transform of small x. I'll take later Laplace inverse to get small x. So from this, the following can follow, students. So Laplace inverse of x is going to be like this. Look, it has been already decomposed, and we obtain 3 values here. You see, a was, you see, this 1 minus 2, and b, c, all are obtained, and we decomposed them as you see. So using decomposition and simplification, one can obtain Laplace inverse of x to be like this. You see, this can enable us to know what x of t is. And we know that 1 over s plus 1, Laplace inverse of 1 over s plus 1 is a power of minus t. And this is Laplace inverse of s over s squared plus 1, which actually is cos t. And for this we have sin t. So basically when we simplify this comes x of t, and this is minus 2 is a power of minus t, as I said. And this is positive 2 as it is, and cos t minus 2 sin t. So students, now we determined what x of t is. The next one is to determine what y of t is going to be. Once we have x of t, as you see, in order to determine y of t, we have two techniques for that. One is to determine what y of s is, and then after to find the Laplace inverse of y of s. And the other is just to use the equation as it is, okay? To use the equation as it is. We know what y and derivative of x with respect to t are related to each other. So using that, we can determine what y of t is going to be. Let you see. Look, from the first one, from the first equation of the system 1, dx over dt is a power of minus t minus y. So solving this for y is going to be e is a power of minus t minus dx over dt. And we knew what dx is. we knew what x is. So dx over dt is nothing but it's the derivative of this one with respect to t. So derive this and subtract the derivative expression from e to the power of minus t. And this determines what y is going to be. So what comes next is y is equal to e to the power of minus t minus, what is the derivative of x with respect to t? Let's derive it. The derivative of this one is 2 e to the power of minus t. And this is minus 2 sine t, and this is minus 2 cos t. And simplifying this, y of t is going to be e to the power of minus t minus 2, it is negative e to the power of minus t. So this negative makes positive, as you see, positive 2 sine t can come. And again, this negative turns this to be what? Positive. Directly you do have 2 cos t. So students, now x of t and y of t are well known. So the next task is, you see, to consider them as, you see, solutions for the given systems of differential equation. Thus, your x of t is this one, the one that was obtained over here, and your y of t is this one. So students, this Laplace transformation is again very helpful in order to solve systems of equations given as before. I hope you have understood the concept of Laplace transformation in a better way.